Okay, let's take a look here. I want to talk about the last part of chapter 6. There's one short section has to do with some applications of this polynomial stuff we've been talking about. So the first part, well, I'll show you one thing first here. Before we jump into this, I've talked about this a little bit. Quincy, put that away, please. But I want to draw attention to the connection between these terms. Okay, these are vocabulary terms. We use them a lot. I think everybody has probably a pretty good idea what they all mean. But I want to this is out of the book, by the way. You'll find this this is one of the green boxes that's right in the textbook. This is a good one. This is a big one. How are these all connected? Okay, these are all equivalent statements. If we've got, I know that looks ugly, but it just means a polynomial, right? If we've got some f of x is some polynomial function, okay, then the following statements all mean the same thing. They're all linked together. We could say that k is a zero of the polynomial function f, and then remember all that means is k is a value we can plug in for x that makes the value of the function equal to 0, okay? So that's one statement. That's exactly equivalent to saying that x minus k is a factor of the polynomial. And we talked about that. Remember, our recipe for generating a factor from a 0 is just subtract the 0 from x. Okay? Same thing as saying k is a solution of the polynomial equation f of x equals 0. Right? And like we said, that's a 0 because when I plug k in for x, I get back 0 for the value of the function. And then the last one. Now this is important to recognize here that we're only talking about real numbers. If k is a real number, if it's not, this doesn't apply. But if it is a real number, then the following is also true and equivalent to the first three statements. K is an x-intercept of the function. Okay, remember that only if it's a real 0, though, does it correspond to an actual x-intercept. If it's an imaginary 0, it won't show up that way. Okay? So if you're trying to, on one of my tests or some other test, if you have a graphing calculator available and you're trying to find the zeros of a function, if you're asked to find all the zeros, real and imaginary, then x-intercepts aren't going to cover all your bases. For example, what if it were a quadratic equation? If it were a quadratic equation in standard form, and you wanted to find all zeros, real and imaginary, what would you do? Quadratic formula, sure, because it's going to give you both. It's going to give you the real solutions and the imaginary solutions. If you're just looking for the real solutions only, what other option would you have? Well, yeah, you could factor, but say factoring would be hard to do. What else could you do? You could always use the quadratic formula. But if you're just looking for the real zeros, what about this? We could actually just graph it and find the x-intercepts, find where the graph crosses the x-axis. I think initially that's a little bit harder for you to do, to get the window sized right, but eventually that probably will be the way you do it the most. It's pretty simple way to do it. Okay. And the nice thing about it is it works for all functions, not just quadratics or polynomials. It works for any function. If I graph it, and I want to find the real zeros, I just look for the x-intercepts on the graph. Okay? All right. So, new stuff. The last part of chapter 6, we're talking about modeling. We're talking about finding polynomial functions that fit data. This is the chapter 6 analog of stuff we've already done a lot this year. Remember back in chapters 3 and 4, we did some linear regression stuff where we were given a distribution of data and we found the best fit line. Okay, that's the same kind of thing we're doing now. All right, so that's modeling for lines. We did the same stuff in chapter 5. We did quadratic regression, right? Now we can do similar things for bigger polynomials. On your calculator, you may have seen this already, but if you go to the stat menu and you go, here's where you put in data, but if you go to the stat screen calculate menu, well, number 4, the fourth option, linear regression, that was chapter 3 and 4 stuff. The fifth option, quadratic regression, was our chapter 5 stuff, and now we've added a couple more. cubic regression and quartic regression. Cubic just means a third degree polynomial. Quartic means a fourth degree polynomial. But we added, so that's chapter 6 stuff. Okay, we can do the same kinds of regressional analysis, curve fitting, with polynomials that we did with all that other stuff, right? Okay, and we'll do one of those just here in a little bit. Okay, now what about something like this? It says write the cubic function whose graph goes through the points -2, 0, 0, 2, 1, 0, and 3, 0. Yeah, we could. One way we could do this is we could plug those 4 points into the stat editor and just hit cubic regression, and it's going to give us back that cubic polynomial. Okay, there is another way we could do this one. Does anybody notice anything interesting about those 4 points? Yes. Okay, they all have a 0, and in particular, the fact that this one has a 0 is kind of an accident. But what about the other 3?
The zeros for the y.
Okay, yeah, the y values are 0 in each case, so those are zeros of the function, right? So if I were to write this in its factored form, look what this would look like. I know if it's cubic, it's going to have 3 factors, right? If it's cubic, that means that if I were to FOIL this out, I would end up with, when all the dust settled, if I FOIL those 2 out and then distributed this, what's going to be my biggest power of x? If you look ahead, if I FOIL the first 2 out, I'm going to get x squared plus some other stuff, right? Yeah, x cubed, isn't it? I'm going to get, from the first 2, if I FOIL those out, I'm going to get x squared plus other stuff. When I distribute through the x minus 3, when I distribute that x to the x squared term, I'm going to get an x cubed. That's going to be my biggest power of x. I can see that because I've got 1, 2, 3 x's being multiplied together there, right? So if I were to factor this thing, I know that it's going to be each of the factors that go with the zeros, right, times a, some multiplier out in front. This is the cubic equivalent of that intercept form that we had for a quadratic function back in chapter 5, right? This works for all polynomials. I'm just going to have as many factors as there are, as the degree of the polynomial, right? So here are the 3 coordinates that correspond to the zeros because the y values are all 0. Well, I'm just going to be subtracting those. Remember that the factor that goes with a 0 is just x minus that 0. So we're going to have one that's x minus 1. We're going to have one that's x minus 3. And we're going to have one that is x minus -2, so x plus 2. And the only thing left to do would just be to figure out what's that multiplier out in front going to be. And the way I could find that would be if I just plugged in this last point, 0, 2. If I plugged in 0 for x and 2 for y, then the only thing remaining unknown would be that a, wouldn't it? Right? And I could solve for a. There's another way I could do that problem. But I could just put it into my calculator and do cubic regression. Okay? The advantage of this way is, it's not a huge advantage, but the advantage of the way that's shown up here right now is that I can find a even if it's a fraction. Okay? If I use my calculator, it's going to give me back decimal coefficients. But that's the only disadvantage, really, using regression. It would work. Okay, questions on that? Okay, we'll do one example of regression so you can actually see it work before we go today. All right. So another property of polynomials and if we were to plug in the x's and the y's, I guess I didn't really finish this. 0 plus 2 is 2 times -1 times -3 is just 6, right? So I get 2 equals a times 6. If I divide both sides by 6, I get a equals 1/3. So I can plug in 1/3 for a, and there's my answer. Okay, the other thing I wanted to show you is a property of polynomials that's interesting. Now this is actually related to calculus stuff, but we don't need to know the calculus at this point to use this to our advantage. If you take a polynomial function like this one, for example, if I calculate the values of the function for consecutive x's, So I'm going to do something like this. I'm going to calculate f of 1, so the y value that goes with an x value of 1, the y value that goes with an x value of 2, with 3, etc., all the way up to, say, 6. We just need several of them in a row. Here's what I get. If I put 1 into my function, I get back a y value of 6. If I put 2 into my function, I get back a y value of 25. If I put 3 into the function, I get back a y value of 70, etc. Okay? And that's all we're doing there is just evaluating the function. Nothing fancy at all. Just plugging an x value in and figuring out what we get back for that x value. Nothing fancy. Now, when I calculate what's called the differences for a polynomial, all I'm doing is I'm just figuring out how much the y value is growing from one term to the next. So, for example, what is going to be the difference going from the first term to the second term here? How much is the y value growing?
21.
No. 19? Everybody see that? Because 6 plus 19 is 25. What's the difference between the second and third terms?
35.
No.
45.
45? Okay, now what's the easiest recipe for finding differences then?
Subtraction.
Yeah, I'm just going to always subtract the left value from the right value as I move along. Right? 25 minus 6 is 19. 70 minus 25 is 45, etc. Right? Okay, subtract left from right. And here's what I would get if I went through all those, if I found all the differences. Now, these are what we call the first order differences because we've only subtracted once. Okay? I can keep going with this, though. I can take the answers I got for my first order differences and subtract those and find the second order differences. So 45 minus 19, 83 minus 45, etc. And I get those numbers. Okay, those are my second order differences. Well, what am I doing? Why do I keep going with this?
Because you want to try
You'll
to
see.
find one.
You'll see. Now watch, if I go again, they're all the same. Okay, the third order differences are constant. Now, we could have predicted that because does anybody see a number 3 in this in my original polynomial that might be significant here? Where's the significant? It took us 3 differences, so the fact that we've got third order differences is predictable. Where does that 3 show up?
And subscript.
You mean in the superscript?
Yeah.
In the power, yeah. It's a third order polynomial. The biggest power of x is 3. Okay, so whatever the degree of the polynomial is, that's exactly how many differences we're going to have to calculate to get back a constant value. Okay? It always will work that way. Okay? Now you might be thinking, well, big deal. Why is that so helpful? Here's why it's so helpful. Let's say we want to go backwards with this. Let's say we've got the data and we don't have the polynomial, but we have the data points, and we want to calculate what's the simplest polynomial that fits that data. Okay, like in this case, for example. Here's the data. We don't know what the polynomial is. We want to try to find the polynomial function. Now, what's going to happen if I put this into my calculator? Let's just see if we do some regression on this. Let's see what happens. Okay, so if I put in, let's get out of there. I want to go to the stat editor and put this data in. So, okay, I've already got it in there. What are the odds of that? X is, now notice these are ordered pairs. When X is 1, Y is negative 2. So everybody, remember that all this means I can take this information right here and think of that as an ordered pair if I want to. X value, Y value, right? So there's my first ordered pair, there's my second ordered pair, there's my third ordered pair, and if I scoot over, oops, there's the fourth one, fifth one, and then sixth one. Okay, so I've got all that data in there. Now watch what happens if I do regression on this. If I do stat calc, let's start off with, how about quadratic regression? See what happens. If I do 5 for quadratic regression, I'm going to store this as, how about y2, 2 for quadratic. Okay. And it look at that, r squared is 1, perfect fit. Okay. And if I go up here, I go zoom data, there's my quadratic function. Okay. But watch what happens. If I do the same thing, I can use the very same data that I've already got in there. And if I do cubic regression, so I'm going to choose 6. Cubic regression, and I'll store that as y3. Ah, what do you know? R squared is 1 again. Okay, it works. It's also a perfect fit. Okay, so what if I do, quartic regression? What do you think is going to happen? Same thing. Store it as y4, how about? And then we'll look at what these things look like if I extend out a bit. Okay, as you might have expected, once again, I get, if I go down, r squared equals 1. Perfect fit. So which is really the best of the 3? I'll let you answer now. If we go back to the original graph, and I look at all those graphs superimposed, there's the quadratic one, there's the cubic one, there's the quartic one. You can't even tell the difference. But what if I extend out there quite a ways? If I let the window go, instead of going from 0.5 to 6.5, what if I go from negative 50 up to 60? And I'll just go zoom fit. Okay, now watch these graphs. Hope this works. There's the first one. Okay. I think I maybe picked a bad example, actually. Picked one where they're all going to overlap pretty well. Well, I'll come up with a better one for some other day. What could happen, though, what can happen with this is, if I take the more, the higher order polynomials that I fit this to, the more jumpy the graph is going to get. I think the reason this worked is because it was a perfect fit. But what we're going to find is, if we were just fitting data that wasn't perfect, a lot of times what's going to happen is, let's just pretend I did a quadratic fit and I got a 99.7% fit. And then I go up to cubic and quartic and it gets a little bit better. Well, what would be the best answer? The one with the tightest fit, with the value of r squared that's going to be closest to 1? Not necessarily. What we really want to think about this is, we want to find the first polynomial fit that's going to do the job, so to speak. That's going to give us a really pretty solid fit. If we jump up from 85% up to 99.5% on the next one, that's going to be our winner. If I keep using higher order polynomials for my fits, of course r squared is always going to go up, but when I look at the graph, it's going to start to get really jumpy, and that's not what we want. We want the smoothest fit that we can have that matches the data. We're not going to spend a ton of time with this year, but this is the kind of thing that, as you go on in math, this is the kind of analysis that most people do. Most people don't spend a lot of time doing algebra, but they do. This is the kind of stuff that most jobs, at some level, could actually do some of, and that's curve fitting, where you've got some data, and you want to find out what's the function. I don't even really have to know necessarily everything about that function, but I have to know the formula so I can make predictions. If I'm in a business and I'm predicting revenue, for example, I want to find the curve that matches revenue the best so I can say, okay, now what's going to happen if I ramp up production another million, whatever I'm making, another million products, what's going to happen? I better know pretty confidently, because I'm spending lots of money and lots of people's jobs are on the line. And so that's where the curve fitting starts to be more important. Okay, so anyway, I digress. How can we, back to this topic here, how can we use what we just talked about to help us out in this case? Well, what we can do is we can calculate the differences, and well, let's see what happens if we calculate the differences here. If I calculate the first order differences in this case, what do I get? Well, 2 minus negative 2 is 4, 12 minus 2 is 10, etc. So my first order differences were these numbers. The second order differences, though, look what happens. The second order differences are constant. So what's the degree of the polynomial that we should use? 2. Yeah, not 3 or 4. We should use 2 because it was only, here's our first. Second order differences are where we got constants. So then now what I can do is go back to my calculator now and know which type of regression to use. I'm going to use the quadratic one because that's the one that goes with the second order polynomial. Now what if we had to go down 1, 2, 3, 4 before we got to constant differences? Which type of regression would we have used then? Which one goes with fourth order? No, cubic was 3. Quartic was 4. Remember, 4 quarters in a dollar, so quartic is 4. Okay? All right? That's what we do. All right. I think that's all I really probably want to do. That should cover all our bases, yeah. Okay. All right, why don't you go practice this? We'll go to the lab.